Hey. Hi, Miss Murphy. Hey, how are you? Okay, we are going to discuss this time the ideal gas law related to density and molar mass. All right, so we're going to derive an equation. All right, and I'm going to reference the practice problems that I posted on your Google Classroom with this video. So there's only two. Oh, I hate it when that happens. Doom, doom. Okay, ready to go? Got my brown paper again. Let's do this. Gray. How's that color? Yeah. Ideal gas law, density, and molar mass. All right. So we know that the ideal gas law, right, an equation of state PV equals nRT. Now let's derive an equation for density and molar mass in here. Now, let's look at density. Density is a measurement of mass per unit volume, all right? For gases, this is typically grams per liters, all right? Whereas for solids or liquids, it's typically grams per milliliters. But gases take up so much space that it's grams per liters. Molar mass, it is the mass of a mole. So that is mass per mole. And we see that unit in grams per mole. All right? Now, I want you to think about something else. N stands for moles, right? And if I was to ask you to calculate the moles of something, you would take the grams given and you would divide it by the molar mass. And that would equal your number of moles, okay? So what we're doing, guys, is we are deriving an equation. If we take the ideal gas law, PV equals N, and in place of N, we plug in mass over molar mass, because when we solve for N, do you not essentially take your grams and divide your grams by the molar mass? That will give you the number of moles, all right? So in terms of moles, I'm going to write mass over molar mass, all right, in place of N. And then I will write RT. I now have an equation that has molar mass in it. So let me rewrite this. PV equals mass RT over molar mass. Well, if I do a little bit of algebra, I see that molar mass equals mass RT over PV. I can now solve for the molar mass and identify the gas. All right. All right. So there's a new equation we have derived right here from the ideal gas law that allows us to solve for the molar mass. Let's look at how we could take the ideal gas law and use it to solve for something such as density, okay? Okay, well, let's rewrite this equation and let's derive it. PV equals mass RT over molar mass. All right, well, look what density is, right? We defined density to be mass per unit volume. Well, in our equation, we've got a mass and we've got a volume. If we can rearrange this so that the mass is on top of the volume, we can redefine that as density, right? Because mass divided by volume is density. So what I will do, right, mathematically, is just multiply both sides by molar mass, and I will then divide both sides by the volume, right? And what I end up with then is molar mass times the pressure equals the mass RT over V, okay? Now look at this. Mass over volume is what? Density, right? This is density equals density. So we can rewrite this. So molar mass times the pressure equals the density RT. We can divide both sides by the pressure, right? Then we have dirty P. We now have an equation that contains both the molar mass and the density. We could rearrange to solve for density by saying molar mass times pressure over RT. All right, so we have taken the ideal gas law, and from that, we've created equations that involve both the density and the molar mass. All right, so we've got a wealth of equations at our fingertips. Let's see what this little practice problem here says. Let's move him down a little bit. Oops. Using the equation derived above, okay, we can do that. Determine the density of CO2 at 745 millimeters mercury. So that is our pressure. And we have 65 degrees Celsius. Oh, let's go ahead and add 273 to that. Remember, we don't need a Celsius. And that gives us 338 kelvins, and that is our temperature. So we need the density. So that's D equals molar mass, pressure, RT. Well, it looks like we have everything there except for the molar mass. So our molar mass will be equal to 44.01 because we are dealing with carbon dioxide. So we go to the periodic table and we add up the 1 carbon and the 2 oxygens. Now you see we can plug everything in. Density equals, let's pay close attention to our units. All right, there's our molar mass. Let's look at our pressure, 745 mmHg. So I need to use my R value for millimeters mercury. That is 62 point, oh gosh, 4 or 3, 4 liters mmHg moles kelvins. Sometimes, never mind, I changed my pressure to atmospheres and plug in my R value for atmospheres because I know it better. And my temperature here is 338 kelvins. Let's look at our units. I know a lot of you don't like to stop and do that, but let's do it. mmHg, kelvins, kelvins, mole, mole. Look at what is left over. Grams per liter, perfectly appropriate for density. Yay, okay? It says appropriate unit, yay. That's what I wrote right there. Appropriate unit, yay. All right, grams per liter. go ahead and do the math. 44 times 745 equals, divided by parentheses, 62.4 times 338, close parentheses. And it looks like we have a density here that is 1.55 grams per liter. Okay. All right, let's go to the last one here. And we have a sample of gas with a mass of 2.929 grams, occupies a volume of 426 milliliters. Well, I know that I'm using the ideal gas law and I cannot use milliliters, so I'll change those to liters. At 0 degrees Celsius, well, let's go ahead and change that to kelvins. And a pressure of 1.00 atmospheres. What is the molecular weight? That means molar mass equals question mark. Well, this is how you memorize this equation. Did you hear how I said it earlier? Look right here. Dirty P, right? Dirty P. So our molar mass, let's watch our units, is equal to our density. Well, remember that density is equal to mass over volume. And that's what they've given here. They've given us a mass and a volume. So I'm going to plug my density in as such. So I'm going to plug my mass in at top. That's the 2.929 grams. I'm going to plug in my R value. Our pressure is in atmospheres, so R is 0.08206 liters, atmospheres, moles, Kelvin. All right. Plug in your temperature in kelvins. It's 273 kelvins. All right. We need to, down here, put in our volume. It is 0.426 liters, and our pressure, which is 1.00 atmospheres. Now let's look at our units and see that they give us the units that we need for molar mass. All right. Let's see. Atmospheres, gone. Kelvins, gone. Liters, gone. We're left with grams per mole. And that is a perfect, appropriate unit. Okay, so that's a good sign. We know that all we need to do is what we've set up here, and it should give us the right answer. 2.929 times 0.08206 times 273 equals, divided by, I'm not going to use the 1, so just 0.426 equals. And that is 154. Look at your exponent over there. And our units are grams per mole. So I could possibly identify what this gas is. It looks like a rather heavy gas, right? But that would be your molar mass.